In this video, we'll pick up where we left off with properties of logs and use those properties to solve equations. There'll be some more haikus as well. In our first example, we're asked to solve for x, and the equation is log base 4 of x minus log base 4 of x minus 1 is equal to 1/2. To solve this equation, I'll start by using the quotient rule, since the logs on the left-hand side of the equation have the same base. That allows me to rewrite this as log base 4 of the quotient x divided by x minus 1. And this, of course, is equal to 1/2. In my next step, I will get this out of logarithmic form into exponential form by raising the base 4 to 1/2, giving me 2. 4 to the half power is 2, and that's equal to x over x minus 1. From here, I can proceed as I normally would, maybe multiplying both sides by an x minus 1 to get this. Distributing a 2 gives me this equation, and thus 2 would be equal to x. It's always good to check the solution. When I plug 2 back in for x, I see I get log base 4 of 2, which asks which power should I raise 4 to get to 2. It's just the half power, minus log base 4 of 1. And which power should I raise 4 to get 1? That's just 0. So half minus 0 is indeed a half. That checks out. As with the last video, the haikus often offer a bit of wisdom. Always remember, extraneous solutions are lurking. Check your work. We'll use that advice in this example. In this example, I'll get things started with the product rule, since the logs on the left-hand side both are base 3. That will give me the equation log base 3 of x times x plus 6, which is x squared plus 6x, is equal to 3. Once again, I'm in logarithmic form. When I put this in exponential form, I find that the argument x squared plus 6x is equal to 3 cubed, and that's 27. And thus I can say x squared plus 6x minus 27 is equal to 0. Factoring tells me that x plus 9, x minus 3 is 0, which leads me to the conclusion that x is either -9 or positive 3. And when I go and I check, I notice that -9 will give me a negative argument here and also here, right? And a negative argument, in fact, any argument less than or equal to 0 is not permitted for a log. So there's my extraneous solution. Plugging in 3 works out just fine, since log base 3 of 3 is 1, and log base 3 of 9 is 2, and 1 plus 2 is 3. So 3 checks out, but -9 is no good. We'll also look at a couple exponential equations and see that these can be challenging in their own right, starting with this next example. In this example, we're asked to solve for x when 12 to the x is equal to 4 to the x plus 2. Okay, so this is a job for a logarithm because I have variables in the exponent. And one strategy that I won't use in this video, but you can try it, is just taking the log of both sides. You can use any base that you want on the log. You can use base 10, base 12, base 4. If I just write it like this, kind of show you how this would play out if I were to take the log of both sides. What I'd then be able to do is I'd be able to linearize this equation, because the power rule would allow these both to come down and multiply. And now it's a linear equation. It's a little bit of a messy linear equation to solve, though, because there's still logs involved. It's not a log of a variable anymore, but a log of 12 will be involved, which is some hideous looking constant, and log of 4 would be involved, which is also pretty hideous. So there is sometimes a better way to solve these exponential equations. And I'd like to show you that here. I noticed that 12 is 4 times 3. So that's 4 times 3 to the x. And on the right-hand side, it's 4 to the x plus 2, which of course is 4 to the second times 4 to the x. All right, so 2 plus x. Now when I simplify on the left, I get 4 to the x times 3 to the x. And on the right, of course, I just get 16 times 4 to the x. Okay, now I'm left with a 4 to the x on both sides of the equation, and I can safely divide that out since an exponential is never equal to 0, leaving me with the equation 3 to the x is equal to 16, and therefore my x is equal to log base 3 of 16. So there's a couple advantages of doing things this way. And it doesn't always work out nicely because in this case, base 12 and base 4, 12 contains a factor of 4, which nicely canceled out. If I didn't do it that way, if I used the original approach where I just kind of brute force, take the log of both sides right at the very beginning, often the answer gets kind of messy, right? And if you're approximating your answer, then no big deal that it's messy. Punch it into the machine and see what it's equal to. But if you want a nice kind of clean looking answer, then consider what the bases of those exponentials are, and can you do any simplification beforehand to make your life a little bit easier. In this next example, we'll see some more challenging exponential equations that we can still solve. Logs and exponents can hide in quadratic forms, and we're told to try to use substitution. So this word, quadratic forms, what it means is there's a quadratic equation going on, but it doesn't necessarily knock us in the face, smack us in the head that it's a quadratic equation. We need to maybe use some substitution to recognize that there is actually a quadratic hiding here. Let's see. In this example, I see a rather complicated looking quadratic form. And if I solve this problem at the onset, I don't think I'd automatically think, oh, this is a quadratic form, I should factor it and solve. Instead, it looks like maybe I need logs right off the bat. But let me show you with a little bit of rewriting that this in fact is a quadratic. So let's look at this first term. That's 5 to the 2x plus 1. I can rewrite that as 5 to the first power times 5 to the 2x power, because 1 plus 2x is the same as 2x plus 1. Now the middle term, I'm going to leave that alone. I'm actually just going to rewrite this whole equation. Just want to point out that you shouldn't be at any point multiplying 26 by 5 and calling that 130 to the x, because we know PEMDAS and exponents come before multiplication. All right, now let me do another rewrite here. When I see 5 to the 2x, I know that that actually is 5 to the x squared, because 5 to the x to the second power would be 5 to the x times 2, and that's 2x. So all this work that I'm doing is convincing you that there's actually a quadratic equation hiding here. And if you haven't seen it just yet, then I'm going to rewrite it one more time. This time I'll just do it with a substitution. My substitution is going to be a happy face. I got 5 happy face squared minus 26 happy face plus 5 is 0. Of course, the happy face that I'm referring to is 5 to the x. Once I've done that substitution, I see that this is actually a quadratic, and it can be factored, right? And if I didn't see how to factor it, I could also use the quadratic formula, but I don't think this one's too tough to factor. It would be 5 happies times 1 happy to get 5 happies squared. And then since the c term is prime, I only have 2 options really. Is it minus 5 minus 1, or is it minus 1 minus 5? And minus 1 minus 5 is what would get me the right middle term. This is smile there. Okay, so what I now know is that happy face is either equal to 1/5 from the first factor, or happy face is equal to 5 from the second factor. And then I put my 5 to the x back and solve for x, because the problem was to solve, the instructions were to solve for x. So I can see that x either equals -1 or x is equal to +1. And both of these solutions work. You can plug them back in and check. There's nothing extraneous here since the domain of exponentials is all real numbers. We'll wrap this video up with one last haiku and then one last problem. What is harder than logarithmic equations? Log systems, of course. That just sounds so exciting. So in our last example here, I have a quick correction. I'm solving for x. I've got a system of equations. The first equation is logarithmic, log base 5 of x plus log base 5 of y equals 2. And my second equation is 4x plus y is equal to 20. Just quick change there to make this work out a little nicer. So the idea here is to try substitution. If I could take my second equation, rewrite it as y is equal to 20 minus 4x, then I can plug 20 minus 4x in for y in the first equation to get a new equation that is entirely in x. Log base 5 of x plus log base 5 of 20 minus 4x, that's going to be equal to 2. Using my product rule for logs, I can rewrite this as log base 5 of 20x minus 4x squared, and that's equal to 2. Putting this logarithmic form into exponential form, I take the base of 5, raise it to the second power to get 25, and set that equal to the argument to get 20x minus 4x squared is equal to 25. A little regrouping tells me then that 4x squared minus 20x plus 25 is equal to 0, which is to say that 2x minus 5 squared is equal to 0, and x is equal to 5 halves. If x is equal to 5 halves and 4x plus y is equal to 20, then y is equal to 20 minus 4 times 5 halves, which means y is 10. And thus my final answer is 5 halves for x, 10 for y, and we're done here. Hope you enjoyed it.